Hello everyone, my name is Muhammad Farhan and today I am going to solve the nearest diet challenge. So here is the link of the channel if you want to see. So let's get started. So the problem statement for this coding challenge is family likes to eat a lot of biscuits, and depending upon the number of biscuits everyone eats, the family members arrange themselves in unique sitting positions. First, the father eats n number of biscuits, then each family member eats varying number of biscuits. Suppose a family member eats x number of biscuits, then if x is greater than n, that means that person eats uh, more number of biscuits than the father, then that member will sit above the father. And if x is less than n, then that member will sit below the father because he has eaten less number of biscuits than the father. At last, a family member says that I ate y number of biscuits. So we have to find the number of biscuits eaten by a family member which is nearest to the y number of biscuits. So the next slide will make it more clear to us. So this is the whole scenario. You can see 7 circles on the screen, and the first circle and each circle contain the number of biscuits that the family members consumed. Okay, so the first circle contains the number of biscuits that the father ate, and sorry, and these numbers 1, 2, 3, 4, 5, 6, 7 is the serial number in which the family member ate the biscuits. Okay, so first the father ate the biscuits, and since the second member ate 15 biscuits, so it has been placed below the father. And then on the third number, the family member ate 150 biscuits, so he or she is placed above the father. The same case goes for the fourth. Uh, this family member eats 20 biscuits, so which is below less than the father. So but there was already 50 and it is also less than 50, so it comes under the 50. And in the similar fashion all the circles are arranged like this. So this is the sitting arrangement of the family. But now the what we have to do in this question is uh, there is another family member which says that I ate 120 biscuits here. Okay, so we have to find the number of biscuits which is nearest to this 120. And because we have human brain, of course, so we can directly see that 130 is that number of biscuits which is the nearest to 130. But we have to write a computer program to solve this question. So what could be the solution for this problem? So stay tuned for this. So you know what, we can solve this problem using binary search trees. Okay, so we are going to use binary search trees to solve this problem because it can be solved using this. Okay, see, the solution is like this. We will maintain a binary search tree for this problem, and for we know that for any node in a binary search tree, the left subtree has smaller values than that node, and the right subtree for any node in a binary search tree has larger values than that node. So this is the same case and that we can use for this problem. And as you can see, all the if this is the root, then all the values in the left subtree are less than this, and all the values on the right subtree are greater than this 100. Okay, so this can be used for this. So now what we will be doing to find the number of biscuits which are nearest to the input biscuits, we will search for that biscuit. Let's get to the next slide that will make more clear to you. See, in this slide we can see that we have to find the nearest number of biscuits which are closer to 120. Okay, so we know that in a binary search tree, while we are searching, we will search for this 120 in this binary search tree. But as we know that this 120 does not exist in this tree, but uh, we will eventually, end up with no element at the last of the search. So the searching will go through like this. We will start from the node that is 100, and then we will compare, we will check if this node contains this 120 or not, and we can see that it contains 100 and we are searching for 120, so it doesn't match. Then we know that 120 is greater than 100. That means it will be available in the right subtree of this binary search tree. So we will start searching for it in the right subtree. So we will move to the 150 node, and here we will again check if it is equal to 120. Of course it is not equal to 120. So what we will do, we will again check whether it is smaller or greater than 150. So as we know 150 is greater than 120, that means 120 will be somewhere in the left subtree. So we will end up with the 130 node. So in this node we will again compare 130 with 120, and they doesn't match. They sorry. So the 130 is a leaf node. That means it has no children further. Okay, that means we don't find any 120 in this binary search tree. So now one thing that I want to tell you that is that while searching for the tree, what we did is that we moved towards a specific path. You can see here, first we move here, then here, then here. Okay, so as we were on each node, like we were on the 100, so we maintained a list. As you can see here on the top left corner, we maintained a list in which what we added is we added key value pairs of biscuits and the diet difference. Now what are these two things? The biscuits is the number of biscuits in each node. Okay, suppose if you see the first key value pair, this is 120. So 100 is the number of biscuits in the first node, root node. Okay, so 100 is this. Now what is 20? 20 is the diet difference. That means this is the number of biscuits that the family, that the father ate. Okay, and this is the number of biscuits that another family member ate, and the difference between their biscuit diet is 20. So we can see the value for this key is 20. Similarly, when we visited the next node, it has 150 biscuits. So we pushed the 150 in this list and stored 30 as the diet difference between these two. As we can see, the diet difference is 30 between 150 and 120. And then finally we end up with 130, and the diet difference is 10 between these two. So in this manner we end up with a list which has key value pairs, and we have the minimum diet difference with the 130 key. So we got our answer. That means 130 is the number of biscuits that is nearest to this 120. So the complexity of this solution is the time complexity is big O of log n, because when we are on each node we are dividing the problem in half. Okay, in each step, like when we were on 100 we divided the problem in half by only moving into the right subtree. When we were on 150 we moved only to the left subtree, so each time the problem is getting a half of its size, so the complexity is big of log n. Now talk is cheap, show me the code, use dark theme for your code, otherwise people are gonna laugh at you. So these are some funny codes, some programmer things. Now let the code begins. Now I have written the code for this solution in Python. So here I have made a class node. This is the constructor for this class, and whenever we make an object of this class we have to pass data, the number of biscuits uh, in the node, because the node contains it. And we can see that here the node has three properties here: the data, the left link, and the right link. Okay, so we are going to have these three properties in each node, for each node. Okay, so for each node we will be having the data, the left node and the right node, and in the starting the left and right nodes will be null. Okay, then I have defined an insert function to insert new nodes, and if the root and the insert function will take two parameters: the root node, because whenever we want to insert any node we should be starting from the root node to check the position of the node that we are going to insert. And the second thing it is going to take is the node itself. Okay, so if the root is none, that means there is nothing in the root, then we will make the that means this is the initial node and we will make it the root node. Else if we already have a root node, then what we will do, we will check that the data of the root node is less than the data of the new node that we are inserting in the binary search tree. So if this is the case, if the data of the root is less than the data of the new node, then we will check if the right portion of the root is none or not. If it is none, that means it has no children, then we will assign it the new node. Okay, but if this is not the case, then we will use the recursion to insert this node on the right side of the root, because that means it has some children on the right side, and then we will use the recursion to insert that node onto the right subtree of the root node. Okay, else what we will be doing, we will be checking that else means the data of the root is greater than the data of the new node. That means therefore we are in this else block scope. So we will check if the left of the root is none, that means it has nothing, and if it has nothing, then we will assign something to it. Sorry, not something, the this node that we are inserting to the left of the root. But if the left of the root is not empty, that means it has something there, then using recursion we will again call this function on the left sub part of the root, left subtree of the root, and we will pass the this node as the second argument. Now this dat difference is a dictionary that we are using to keep the key value pairs. Okay, so as you can see here, comment dictionary to store difference between current node biscuits and the input number of biscuits, the same thing that I explained before. Now this is a search function, and it will also take the root and the data. So because the search starts from the root and we need some data to search the data, that is obvious. So now we will check if the root itself is the data inside the root is the data or not. We will check it. And now here is the part. Here in the diet diff we are storing the root.data as the key, that means the number of biscuits, and we are assigning it the value of root.data minus data, and I'm using the absolute function to remove the complexity so that my uh, difference is always positive. Okay, and then I'm returning the root.data. Okay, simple. Now if the root.data is less than the data, then I'm checking if the right part of if there exists a right part of the root, that means the right part of the root should not be none. And then again I'm doing the same thing. I'm uh, storing the key value pairs of these, and I'm recursively calling the search function again, because what we can see here is that here the root.data was smaller than the data, that means it is smaller. Okay, so we are returning the search root.right to recursively search on the right side of the root itself further. Okay, and in the else case, that means if there is no right part of the root, we are storing the key value pairs and returning from this function. Okay, now in the else part we are checking the same thing for the left part. If there exists left subpart or subtree of the root, then we are doing the same thing. We are storing the key value pairs, and again we are recursively calling the search function on the left part of the root with the same data that we are searching. Else uh, we are doing the same thing. We are storing the key value pairs in the dictionary, in the tag difference dictionary, and we are returning from this function. Now this is the function which calls the actual, which gives us the actual result, the find nearest type. It also takes the root and the data, and it calls the search function. It calls the search function, and here you can see that the nearest tide is the result that we want, and we are getting it from the tide difference. Now this tide difference is the list which we have got, which was this list. Okay, now we have got this list, and now we want to extract the uh, key having the minimum value. Okay, so generally what happens is that this minimum function returns us the key which is minimum, but we are using here a lambda function. Okay, we are utilizing a lambda function to get the key which has minimum value. Okay, so that's why we are passing the direct difference, and we get the key with the minimum value here, and we are returning that nearest type. So now these were all the definition of the functions, but the execution of the program starts here by the interpreter. See, we are making a node object from the node class, and we are passing 100 into it. That means we have created our first node, root node, that the father ate the number of biscuits, 100, and we are assigning it as root. And then we are inserting 50, 20, 60, 150, and so on number of nodes in the binary search tree using the insert function. Now the nodes will be inserted in their respective places, and we will get a structure like this that we had, and then we will call the find nearest type function, which takes two parameters, root and the data which we want to find. This is the number of biscuits. which we want to find the nearest number of biscuits to which. Okay, so now the find nearest function will take root as root and the data will be 120. Now it will call the search function and pass the root its root to this, and the data will be passed as it is in the search function. So now the search function is called, and the condition is checked if the root dot data is equal to the data, and we know that the root dot data is 100 and it is not equal to 120, so it will skip this condition and it will check this, that the root dot data that is 100 and it is less than 120, so it will execute this block of statements. So now it will check if the root has a right part, of course it has, and then it will, in the dictionary, that difference dictionary, it will store the root of data that is 100, and it will store it as the key, and the value would be the difference between the 120 and the 100, that would be stored as a key value pair of 120. And then we will search again to the right part of the root, the right part of the subtree, okay, sorry, the right subtree of the root recursively, and again this procedure will go on and we will have the values stored in our dictionary. And now this else part is because we are not able to find the uh, element, we are not able to find the element which we want to find, and it doesn't exist, and that means that is the leaf node. Okay, it doesn't have any children, so it has no children, but we still want to store it in the dictionary. That's why we are doing this, and we are returning nothing, but we are returning ourselves from this function. Okay, so now the find nearest diet function, the search will be completed, and we will now we have a diet diff, which is a dictionary of key value pairs, as we know. And now what this main function does is, this main function returns us the minimum key, the key which is minimum. Okay, but what we want is the key which has minimum value. The key should not be minimum itself, it should has minimum value. So that's why we are using a lambda function, which is helping us to do that. We are passing the diet difference dictionary in it, and we are passing a key as a key. We are using a lambda expression which is taking k as a variable, and this variable is going into the dictionary, and then this main function is returning us the key having the minimum value, and then we have that value in this, and which is whatever we find. In this case it is 120, so it should be 130. Now nearest type is 130, and it returns the nearest type, and we then accepts in this variable, and then sorry and then we print the nearest type result here using the format string method, format string. Okay, so now thank you, I was Mohammed Farhan, and thank you Hitesh sir for giving us such opportunities. And now let's check whether this works or not. Okay, so this is the same code. Okay, as you can see, this is the same code. Now I'll be searching here for, first let's search for 120. Okay, and let's run this program. So python 3 and solution.py, and you can see the result is 130 for this, and this is the diet diff dictionary. Okay, and let's run it for 90 and see the result is 100, which is true. 100 is the nearest diet of biscuits. So thank you very much. Thank you.